All right, so lesson 2B is going to be all about inverses, inverse functions, the derivatives of inverse functions, and also some trig inverse derivatives, which are kind of beastie. So just some notation that we don't want to forget. So the inverse of sine is sine negative 1x or arc sine. The inverse of tangent would be written as tan negative 1x or arc tan, and the same applies to all the other trig functions as well. So the same thing applies to cosine and secant and cosecant and all those functions. I just wanted you to make sure you didn't forget about that notation. So here are the trig inverse derivatives. So you just have to memorize them. You can derive them, but it is a long process. You would actually use what we're gonna learn in a few slides, which is the derivative of an inverse kind of setup there, and you would use it to actually get these specific derivatives. But for your purposes, we're just going to memorize them. So a couple of things to kind of help. A lot of them are very similar. So when you're looking at sine and cosine, they are the same. It's just cosine is negative, which we know are cos. If you look at all the cos here listed, they're all negative. Now here, so sometimes this value is just x, which means the derivative with respect to x would just be 1. So a lot of times you don't have to do this little piece right here, the du dx. But if there's like a function inside of here, then you would leave the function inside like as u, and then you would multiply by the derivative of that function. So essentially it's just a chain rule. So we have the sine and the cosine, very similar. Just the cosine is going to be negative. Same thing with the tangent and the cotangent. They're the exact same. It's just one of them is negative. What I remember is that when you have the square root, you have subtraction between them, but the cosecant and the secant, their orders switched. So in those, the u comes first, the u squared comes first, and then the 1 comes second, and the secant and the cosecant, versus the sine and the cosine. Secant and cosecant also have this absolute value of u on the outside there that's being multiplied with that denominator. So kind of some messy functions, or messy derivatives, but they're just things that you have to memorize. They're not like a huge part of the AP Calc exam, but they will show up in a couple of multiple choice questions, or possibly even in a free response question if you're having to find the derivative as part of one. So do memorize them. I'm going to probably have to reference this page quite a bit just because I don't have them memorized completely. It's been a couple years since I've used them consistently, or about a year since I've used them consistently. And when you're not using them, you forget them. But the more you practice with them, the less you'll just have to memorize because they're just going to stick in your mind, okay? And the more we practice with these, the more you're gonna have them memorized. But there's some tricks and stuff to memorize in them. I'm sure you can find some little tricks online, just like you did with the unit circle, to kind of help you memorize them and keep them each straight. We're going to use sine and cosine a lot. We're also going to use tangent a lot. You won't see the other ones as much, the cosecant, the secant, and the cotangent, but the sine, cosine, and tangent, you'll have those memorized pretty quickly. And then just remember the cotangent's the same thing as tangent. It's just a -1 instead of a +1 up top. Alrighty, so we're going to go ahead and use these in a couple of different problems. So here we have 2 times the arc sine of x minus 1. So I'm going to go ahead and take the derivative of this. So here we're going to be using the sine inverse derivative. So it's 1 over the square root of 1 minus u squared. And u squared is going to be whatever's inside the function. So here, for our purposes, for this function, u is going to be x minus 1. I'm not going to label it as u or anything like that. I'm just going to have it inside the derivative when I'm doing the actual problem. All right, so we're going to go ahead and take the derivative here. I'm going to have this 2 out in front, so I'm just going to keep it out in front for now. So I'm going to have 2 times 1 over the square root of 1 minus x minus 1 squared times the derivative of the inside function. But the derivative of this is just going to be 1, so I'm not going to mess with it. I'm going to leave it alone. And then I'm going to clean this up just a little bit. So 2 times 1 is going to be 2, so I'm actually going to have 2 on top. And then I'll have the square root of 1 minus x minus 1 squared. So there's my final derivative for that arcsine function. Delete that little line that I accidentally drew there. All right, and for these, there's not a whole lot of simplifying that occurs. Once you kind of put it into the function, then you're good. So now we're going to do h of x. We're going to find the derivative of h of x. This is x squared times arctan of 5x. Now this one is going to be a product rule. So this one's going to be a little bit more involved because we have two things that are being multiplied together. And we also have a function inside of a function that will have a derivative, because 5x, you can take the derivative of it. So this one's going to be a little bit bigger, a little bit more involved. So I'm going to go to my tangent. This one's pretty easy. This one I tend to memorize a little bit more quickly. So tangent is 1 over 1 plus u squared. There's no square root. Honestly, you could switch up the order and have u squared plus 1. That wouldn't matter because in addition, the order does not matter. So you can have them flip-flopped if you wanted to. So 1 over 1 plus u squared. All right, so let's go ahead and do the product rule. So I'm going to have the derivative of the first function. So I'm going to use some space for this one. So I'm going to come out here to start it. So the derivative of x squared is just going to be 2x, and then I'm going to keep everything else the same. Then I'm going to add the first times the derivative of the second. The derivative of the second is going to be 1 over 1 plus u squared. Okay, u is 5x, so it'll be 5x squared. And then I'm going to multiply by the derivative of 5x, which is just going to be 5. Okay, so now I'm going to try to clean this up a little bit. So I'll have 2x arc tangent of 5x. So I'm going to go ahead and bring the 5 and the x squared on the top of that fraction. So I'm going to have 5x squared over 1 plus, and I'm going to go ahead and square 5x because that's pretty easy. So I'm going to have 25x squared. Now you could get like denominators if you wanted to, but honestly it's not really going to help as far as canceling anything out. So I'm going to leave it just like this. All right, so now we're going to find the derivative of a cosecant inverse. So I'm going to switch back here so you can see the cosecant inverse. It does have the absolute value in it. A lot of times we can pull stuff out of the absolute value if it's not affected, as far as like ever being able to be negative. So that kind of helps being able to cancel some stuff out. Cosecant ones, remember, they're always negative, so it has the negative 1 on top. And then here inside the square root, it's u squared minus 1 instead of 1 minus u squared like it is in sine and cosine. So it'll be negative 1 over the absolute value of u times the square root of u squared minus 1 times the derivative of whatever was inside the function to begin with. All right, so let's go ahead and work on this. So I'm going to start with y prime equals negative 1 is going to be my value on top over the absolute value of the function that's inside, so 4x to the 5th times the square root of that squared, so 4x to the 5th squared minus 1. So there's our function kind of all plugged in. Then we still have to multiply by the derivative of this, which would be 20x to the 4th. All right, so now I'm going to clean this up a little bit. I'm also going to pull out a 4x to the 4th out of my absolute value, because 4x to the 4th is always going to be positive. That additional x that makes it x to the 5th is going to be the one that's going to be affected by the absolute value, because if x is negative, then that needs to be turned positive. And that's just going to allow me to cancel some more stuff out. So I'm going to pull a 4x to the 4th out of the absolute value. So I'm going to rewrite this. It'll be y prime equals negative 20x to the fourth over 4x to the fourth times the absolute value of x times the square root of 4x to the fifth squared, which is 16x to the 10th minus 1. And then right here, I'm going to cancel out the x to the fourths, and then I'm going to cancel out that 4 and change that 20 into a 5. So my final answer there is going to be y prime equals negative 5 all over the absolute value of x times the square root of 16x to the 10th minus 1. Now we have cotangent of negative, or the inverse of cotangent of negative x. So I'm going to go back to my trig inverse derivatives. Cotangent is the same thing as tangent. It's just going to be negative 1 on top. So it's just negative 1 over 1 plus u squared. So I'm going to go ahead and do that one. So I'm going to start when I'm finding the derivative of the inverse of cotangent. I'm going to start with y prime. And I'm going to start with negative 1 on top. And then on bottom, it's 1 plus u squared. So I'm going to have 1 plus u, which is negative x squared. And then I'm going to multiply by the derivative of negative x, which is going to be negative 1. So that negative 1 and that negative 1 are going to end up canceling out and turning into positive 1. And then it'll end up being 1 plus x squared. So that's going to be the derivative of that cotangent inverse function. All right, so now we have a inverse sine function that is actually inside a cubed function, and then it has a cubed function inside of it. So we have a chain rule in addition to a inverse sine function, in addition to another chain rule inside of that sine function, inverse sine function. So we have lots of stuff to deal with. So just as a reminder, sine, the inverse sine derivative is 1 over the square root of 1 minus u squared. So I'm going to go ahead and go to my function. And I'm going to go ahead and start by taking the derivative of the outer function. So f prime of x, I'm going to try to write small so I have lots of space. So I'm going to bring the 3 out in front. And then I'm going to keep everything on the inside. And then I'm going to bump it down to a squared. And now I'm going to multiply by the derivative of sine, which is going to be 1 over, I have to have some space underneath this, the square root of 1 minus u squared times the derivative of the inside, which is going to be 6x squared. All right, now let's see what we can kind of put together and make it look a little bit better. Can't do too much, honestly. So I can put the 6 and the 3 together. So 6 times 3 is going to be 18. And I'll bring that x squared out in front as well. And then I'm going to keep all of this on the top. And then I'll have that square root of 1 minus squared. And that's about all I can do as far as simplifying that one down. So before we move on to the rest of the lesson, I want to review what an inverse is, just so you remember kind of going into the rest of this lesson, which is talking about the derivatives of inverse functions, other than just the trig ones, but other types of inverses, ones that we can actually figure out. So when we're talking about an inverse function, so kind of the most basic definition there, an inverse is a function whose domain of the original function is the range of the inverse, and vice versa. The range of the original function is the domain of the inverse. So essentially what happens when you find a function's inverse is you're switching all the input and the output values. So if you look at these two tables, the one of the original function h of x has the x values 1, 2, 3, 4, and the y values negative 10, negative 8, negative 6, negative 4. And then the inverse h negative 1 of x switches those around. Now here's where we might get a little bit confused as we're going through this unit. We're going through this lesson when we're talking about inverses is remember the inverse notation is a little -1. Please do not confuse that with the derivative notation, which is that little tick mark. Okay, we're going to be seeing both of them at the same time, so just make sure you kind of keep them straight and pay attention if it's a tick or if it's a -1, or it's that prime symbol or the -1 symbol. All right, and then also you can find a function's inverse mathematically or algebraically by actually switching the x and the y values and solving for y, and then you'll have the inverse. So for example, I can rewrite this as x equals y squared minus 8, and then solve this for y. So I'll have x plus 8 equals y squared. So y will equal the square root of 8x plus 8. I was about to write that. Well, I guess I could write the 8 first. It doesn't really matter because they're both addition, but you should write it as x plus 8. So that would actually be the inverse of f. I'm going to switch it around for this one. So that would be x plus 8, the square root of x plus 8. And you know that a quadratic function, its inverse is going to be a square root function. So that's how you can find the inverse algebraically. And then one little note here, when you're looking at the graphs of inverses, a function and its inverse are always reflections across the line y equals x. So because essentially it switches the x and the y values. So whatever like when you switch those two values, you create a function that's just a reflection across that particular line. So notation for inverses, you can always just say g of x is the inverse of f of x if two functions are inverses of each other. If g of x is an inverse of f of x, you can also just use the inverse function to denote it. So you can always use that -1 as an inverse. And then here is another kind of rule or property that inverses have. If you make a composition of a function and its inverse, okay? So if g of x is an inverse of f of x, if you put g of x into f of x, it would simplify down to x, and vice versa. If you put f of x into g of x, it would simplify down to x as well. So I'm going to try that with those two functions that we had on the previous slide. So I'm going to say that f of x is x squared minus 8, and its inverse is g of x, which we found, which was the square root of x plus 8. So I'm going to show this property with these particular functions. So I'm first going to find f of g of x. So I'm going to take g and I'm actually going to substitute it in to f. So I'll end up with the square root of x plus 8 squared minus 8. When I square the square root, it's actually going to make the square root go away. And then 8 minus 8 is going to give me 0, so I'm just going to get x. And then if I do it the other way, and I put f inside g, so I'm going to have the square root of x squared minus 8 plus 8. Here, the minus 8 and the plus 8 are going to cancel out, so I'm just going to have the square root of x squared, which is just going to be x. So you can see that it does work. Okay, that property is true when you have compositions of inverse functions. They end up just giving you x when you find the composition and you simplify it down. All right. Another thing I want to talk about is the derivatives of inverses and how they are related. So let's go ahead and look at two functions. We're going to be looking at the function x squared, and we're going to be looking at the function square root of x that are inverses of each other. So x squared is the original function, and f, not prime, whoops, look, I'm mixing up the notation. The inverse of f is going to be the square root of x. So we have those two functions. Now, when I look at these two functions, I'm going to look at a point on the original function, and then I'm going to look at the same point on the inverse function, but since it's the inverse function, we're going to look at the switched version of that point. And then we're going to compare the derivatives of these two functions at those particular values. So first I'm going to look at the derivative of f of x equals x squared, and I'm specifically going to be looking at that derivative when x is 3. So I'm going to do f prime of x equals 2x, and then I'm going to find f prime of 3, which is going to be 2 times 3. So the derivative of 3 is going to be 6. So the derivative of 3 is going to be 6. So that means the slope of the tangent line at that point. So I'm going to go to the point 39 on my graph, which would be somewhere around here. The slope of the tangent line to that point is going to be positive 6. So the slope is going to be 6 at that particular value. So now let's look at the same point on the inverse function, which is going to be the switched version of that point. So we're actually going to be looking at 9, 3 when we're looking at this particular function. So I'm going to start by actually finding the derivative of this function. Now the notation for this looks a little funky when you find the derivative of an inverse, because we don't put those little symbols right next to each other. We actually use brackets usually. So I'm going to show this a couple different ways. So one way it can look is if you're finding the derivative of an inverse, a lot of times they will take and put brackets around the whole function and then just put the prime on the outside, and then you would find the derivative. Or sometimes you'll see it where they just put the brackets around the f part, put the prime, and then put the x. So there's two different ways you can see it. I think I'm going to write it the first way. I just kind of like the way that looks a little bit better. But you could write it either way, and it would be fine. So you have the inverse notation of the -1 as well as the prime notation for the derivative. So you have both of those notations in that, that notation when you write it out. So I'm going to use that top one. But again, you can use either one. You'll probably see either one. You could also say that the derivative is g of x, and then you could just be finding g prime of x if you wanted to rename the derivative. Rename the inverse completely into a different function. And they tend to do that a lot too. They'll say f of x is the original function, and g of x is the inverse of f of x. And then a lot of times we'll just say g prime of x. But let's go ahead and look at this. So we're going to go ahead and find the derivative of this function. So I'm going to find the derivative of this function. And I'm going to go ahead and remember that this function is the same thing as x to the 1/2. So it's going to be 1/2 x to the -1/2, which is going to be the same thing as 1/2 square roots of x. And then I'm going to be looking at the point 9, 3. So I'm going to be looking at this point right here. And that means the x value that I'm going to be evaluating this at is going to be 9. So x equals 9. It'll be 1/2 times the square root of 9, which will be 1/2 times 3, which is going to be 1/6. So the slope of the tangent line at that particular point is going to be 1/6. So when you look at these two inverse functions, if you know the derivative at one particular point, so if you know the derivative of x equals 3, the derivative at the inverse of that same point, but evaluated for the output, which would be the input in the inverse function, is actually going to be the reciprocal of the slope. So the slope on the original function was 6 at 3, 9. But on the inverse function at 9, 3, the slope of that tangent function was 1, 6. So they're actually going to be reciprocals of each other, or multiplicative inverses, if you want to call them that. So that's just an interesting relationship there. And the actual property for inverses and finding the derivative of inverses actually comes from that idea that they are going to be reciprocals of each other. So here is the derivative of an inverse function. So if you're finding the derivative of an inverse function, it's going to be 1 over the derivative of the original functions taken at the value when you put that x value into the inverse function. So when you plug the x into the inverse function, you're actually getting the output, which would be the input on the original function. So it's kind of confusing when you see it this way to kind of wrap your mind around what's actually happening. But the number you're going to be plugging in to the original function's derivative is going to actually be the output from the inverse function. So it's going to be, so if you're trying to find, for example, okay, if you're trying to find the, like, let's go back to that example that we had, okay? So if you're trying to find the derivative at 9, okay? So if I'm trying to find the derivative at 9, that point on the inverse function is 9, 3. So when I plug 9 into my inverse, I'm going to get out 3. And that means that is the point that I'm plugging into the derivative of the original function, which would give me 6, which means overall the derivative of the inverse function is going to be 1 over 6 at that particular point. But if you don't want to kind of wrap your mind around what it means, you can just memorize this formula. So the derivative of an inverse function is 1 over the original function taken 1 over the derivative of the original function evaluated at the x value. When you plug the x value into the inverse function, the output that you get. Okay, we're going to kind of use this formula a lot through this unit or through this lesson, so you'll kind of get the idea of how you use it in context with an actual problem. Now, this is used a lot when we're doing tables. It's also used a lot when you know like a specific point on the original graph. Honestly, a lot of times it's just going to be easier to actually find the derivative. Find the inverse and then just take the derivative like I did in that first example where I just actually found the derivative of that particular. I knew the derivative x squared was the square root of x, and then I was able to just find the derivative of the square root of x. So you can still do it that way. You can find the inverse of the function and then just take the derivative of it. But this formula is going to be used more, or this property is going to be used more when we're given like a table of values, or if we're given some information about the first function, but not necessarily like the equation of the first function. So you're not able to use it, So it's going to be useful. We're going to use it a lot. But there are other ways you can do these problems too. All right, so let's go ahead and look at a table of values first. So I'm gonna be referencing, of course, this property a lot throughout these next few examples. So example 4 says the table below gives the values of the differentiable functions f, g, and f prime at selected values. And it says that g of x is going to be the inverse of f of x. So if you notice, there is not a g of x column in the table. And that's because g of x is actually kind of its own table. And I can actually make a table for g of x. But g of x is just going to be the inverse of f of x. So I'm going to make a little table out here to the side so you can just see what that would look like. So g of x is the inverse of f of x. So when I make the table for this one, all of these are going to be my input values. And all of these are going to be my output values. So there's my table for g of x. So g of x doesn't fit in line with the x values of that original table. So it's asking for what is the value of g prime of 1. So if I'm trying to figure out the value of g prime of 1, I'm going to go ahead and write down that formula from the previous page, and I'm going to make it look a little bit different to fit the kind of notation of this particular example. So from the previous page, it said dx, so the derivative of f negative 1 of x is going to be equal to 1 over f prime of f negative 1 of x. Now, for this particular problem, it's saying that g is the inverse of f. So I'm going to rewrite this as g prime of x. So g is the inverse, so the derivative of the inverse of x equals 1 over f prime of g of x. Okay. And all I did was replace the inverse here and here with g instead. Okay, so it said the derivative of the inverse of f, and so the derivative of g would just be g prime, and then the derivative of x, or sorry, not the derivative, f, the inverse of f that was inside the parentheses, I just replaced with g of x, which is the inverse of f. All right, so it wants us to find the value of g prime of 1. So I'm going to take this and I'm going to put it into this formula that I just wrote. So I'm going to have g prime of 1 equals 1 over f prime of g of 1. So now I'm going to have to go to my tables and I'm going to have to pick out all of these different values. So I'm going to go ahead and pull g of 1 from this table. So g of 1 is going to be 2. So I'm going to go ahead and replace that. So g prime of 1 equals 1 over f prime of 2. And then f prime of 2 is right here. So it's going to be negative 2. And then it says write an equation for the tangent line to the inverse of f at x equals 1. Okay, so the inverse of f is g, and the point at 1 on g is 1, 2. So I know I'm going to need that. So the point will be 1, 2. And then I know the derivative at 1, which is the slope of the tangent line, is negative 2. So I have all the information I need to write that tangent line equation. So I needed the slope at the slope at the inverse at 1, which was just g prime of 1, and I needed the point from that table. So I'm going to go ahead and say y equals negative 2x plus b, and then I'm going to plug the x and the y from the point in. So I'll have 2 equals negative 2 times 1 plus b. So b is going to be 4. So y equals negative 2x plus 4. That will be the equation of the tangent line on the to the inverse at x equals 1. A lot of times kind of like saying all this stuff and getting the notation right, remember to say the right things, can be kind of cumbersome, but hopefully you're kind of seeing the idea here, okay? Especially when they take and label g as the inverse of f, then you have the inverse of f and g, but they're actually the same thing, okay? All right, so now we're going to do another problem where it gives us a lot of information in the problem, and then we're asked to find the derivative of this h function at 6. So let's see what the relationship between g and h are. So it says let g be a differentiable function such that g of 12 equals 4, g of 3 equals 6, g prime of 12 equals negative 5, g prime of 3 equals negative 2. The function h is differentiable, and h is equal to the inverse of g for all x. What is the value of h prime of 6? Okay, so let's kind of establish here what we have. So first off, g is the original function, and h is the inverse. I'm going to kind of put a little note there. So g of x, that is the OG function, and h of x, that is the inverse function. So that's the inverse, or that is g negative 1 of x. All right, so now let's go ahead and see the information that we have and see how it relates to everything. So I know two values of g. I know that g of 12 equals 4, and I know that g of 3 equals 6. So I can make a little table of values there. I'm going to organize it that way. You don't have to. I'm just trying to organize everything so I can see what information I have. So I'm going to use, I have 3 and 12. I have information at 3, and I have information at 12. And g of x, and I have some information about g prime of x as well. So I know that at 3, g of x is 6, And at 12, g of x is 4. The derivative of g at 3 is negative 2, and the derivative of g at 12 is going to be negative 5. And then since I know that h and g are inverses, I can use this piece of the table, the x values and the g of x values, and I can flip them around. So I can know that x and h of x, when h is 6, h of x is 3, and when x is 4, h of x is 12. Okay, so organized all the information that it gave me in that table. And then I'm trying to find h prime of 6. So since h is the inverse of g, it's going to fit this formula. So it's going to be 1 over g prime of h of x. Okay, and that's just a variation of this formula right here. So it's the 1 over the inverse of the original function, not the inverse, the 1 over the derivative of the original function with the inverse inside. So 1 over the derivative of the original function with the inverse inside. So now I'm going to evaluate this at h prime of 6. So I have 1 over g prime of h of 6. H of 6 is going to be 3, so I'm going to replace that with g prime of 3. And then g prime of 3 is going to be negative 2, so it'll be 1 over negative 2, or negative 1/2. So once you kind of get all the information that you need organized, it's not that hard to kind of go through and pick out like what you have and what you need. So it's kind of easy in that sense. So here we're actually given a function. So we have f of x is 3x cubed plus 1, and g is the inverse function of f. What is the value of g prime of 25? Okay, so if I'm trying to find g prime of 25, I'm going to go ahead and set up the formula first, and then I'm going to see what I need, and then I'm going to use what I have to get what I need. So g prime of x, this is the inverse function. So g is the inverse, f is the original or the OG. So it's going to be 1 over f prime of g of x. And we're trying to find g prime of 25. So that's going to be 1 over f prime of g of 25. Okay, now, I don't know what g of 25 is, but I can figure it out by using the original function, because 25 is going to be an output of the original function, and I just got to figure out what the input is, because then those are going to flip around for the inverse. So I need to figure out when my original function, what x value in my original function will give me, oops, forgot the 1, will give me 25. So I'm going to subtract 1. I'm going to divide by 3. And then I'm going to take the cube root, so x would actually equal 2. So 225 is an x and an f of x value. So when x is 2, f of x is 25. So that means when x is 25, g of x is 2, because they're inverses of each other. So that means g of 25 down here is going to be 2. So I'm actually just looking for f prime of 2. Now I know what f is, so I can very easily find f prime. So f prime of x is going to be 9x squared, and then f prime of 2 is going to be 9 times 2 squared. 2 squared is 4, so that's just going to be 36. So it'll actually be 1 over 36. So for that one, you kind of had to work backwards in a sense to find the input in the original function that gave you that specific output, and then you were able to flip those around to get the output of the inverse function. All right, example 7. So for the given function g of x and its inverse g negative 1 of x, which is equal to f of x, find the derivative. All right, so it does give us some information here, though, that we need. It does tell me that g of pi over 2 is equal to 3 pi squared over 4, which is going to help us in the end. And for this one, the notation might be a little bit more confusing because this time g is the original function and f is the inverse. So it's kind of flip-flop from the previous problems. It's not always going to be the same, so you have to be able to adjust. So for this one, g is the original, so that is the OG, and f is the inverse. All right, so if I'm trying to find the derivative of the inverse, so f prime of x is going to be 1 over g prime of f of x. And I'm trying to find f prime of 3 pi squared over 4, which would be 1 over g prime of f of 3 pi squared over 4. All right, now I know that when I put pi over 2 in for x, I get out 3 pi squared over 4, which means in f, if I put in 3 pi squared over 4, I get out pi over 2 for f of x. So f of 3 pi squared over 4 is just going to be pi over 2. So actually, I'm going to be just trying to find 1 over g prime of pi over 2. And that's what I'm going to use this function for. So I'm going to have to find the derivative of g, and then I'm going to plug pi over 2 into that to actually figure out what the derivative of the inverse function is going to be. So let's go ahead and find the derivative of g. So g prime of x equals negative sine of x plus 6x. And now I'm going to find g prime of pi over 2 equals negative sine of pi over 2 plus 6 times pi over 2. So g prime of pi over 2 is going to be negative sine of pi over 2. Sine of pi over 2 is just going to be 1, so it's going to be negative 1. And then 6 pi over 2 is going to be 3 pi. So it'll be negative 1 plus 3 pi. So then f prime of 3 pi squared over 2, or not 2, 4. Is going to be 1 over negative 1 plus 3 pi. Okay, because I go back and I put this down here, and then I get that final answer. Example 8 is similar to example 9 as far as kind of the information that you're given. So the given function is g of x. So that's the original. So g of x is the original, and f of x is the inverse. And then we're trying to find f prime of 10. So the derivative of the inverse is going to be equal to 1 over the derivative of the original with the inverse inside of it. Okay, so that's going to be that same formula that you're using for every single one. You just have to change it just a little bit to fit the function that you're dealing with. Because if you go back to example 6, g was the inverse, f was the original, so it was flipped around. Okay, but for example 8, g was the inverse. G was the original and f was the inverse. So g prime of f of x was on the bottom versus in this one it was f prime of g of x. So you got to pay attention to which one is the original and which one is the inverse. The inverse is always the one that goes inside, okay, of the the derivative of the original. Okay, so just kind of keep that straight and make sure you pay attention to that, what you're given in the problem. All right, so we're trying to find f prime of 10. Okay, which means that's going to be 1 over g prime of f of 10. So we need to make sure we know what f of 10 is. Negative 10. I wrote 10 for all of those. That's supposed to be negative 10. All right, so, because it's negative here. So we're trying to find f prime, we're trying to find f prime of negative 10, which means we need to know what f of negative 10 is. I know that g of negative 2 is negative 10, which means f of negative 10 is negative 2. I'm not going to draw a table this time, but you kind of get the idea. Inverse flips the inputs and outputs around. So f of negative 10 is going to be negative 2. So I'm going to rewrite this. It's actually going to be 1 over g prime of negative 2. I know what g is, so I can find g prime. So g prime of x is going to be 6x squared minus 2x minus 5. And then I'm going to plug in negative 2. So I'll have 6 times negative 2 squared minus 2 times negative 2 minus 5. So I'm going to end up with 6 times 4 plus 4 minus 5. 24 plus 4 minus 5, which is 23. So I'm going to end up with f prime of negative 10 is going to equal 1 over 23. So once you get the hang of it, the problems can go really quickly, as long as you get that formula set up correctly. All right, and last example that are kind of along those lines, then we're going to do a couple from AP Classroom that kind of are more reasoning questions versus the procedural ones. So now we're going to look at same setup. G is the original. So that's my OG. F is my inverse. So when I set it up, I'm trying to find f prime. So f prime of x is going to be equal to 1 over g prime of f of x. And I'm going to be trying to evaluate this at 1/2. So f prime of 1/2 is going to be equal to 1 over g prime of f of 1/2. Now currently, I don't have any information about f of 1/2. I don't have any information about g of anything, but I do know what g of x is. So here's one that we're going to have to set up similarly to how we did in one of the previous examples where we didn't have the input and the output. But I know that if I'm trying to put 1/2 into the inverse, it was originally an output on the original. So I'm going to take the original function and I'm going to try to figure out what x value would give me an output of 1/2. So what number would I put down here to get 1/2? Now, 1/2 is the same thing as 5 over 10. So I kind of make it match up here. So essentially I'm saying when will x plus 3 equal 10? And that's going to be when x is 7. So that means g of 7 equals 1/2, which means f of 1/2 equals 7. So I'm going to go ahead and put 7 down here. So this would be the same thing as 1 over g prime of 7. Now I'm going to find g prime. So I'm going to have to find the derivative of g of x. So g prime of x, I'm going to do a quotient rule. So I'm going to do the derivative of the top, which is just 0, times the bottom, minus the derivative of the bottom, which is just 1, times the top, all over the bottom squared, which is going to be negative 5 over x plus 3 squared. And then I'm going to evaluate this at 7. So g prime of 7 is going to be negative 5 over, oops, not x, because I'm plugging 7 in. It's taking a minute to switch to the eraser. There we go. So I'm doing 7 plus 3 squared. 7 plus 3 is 10. So it'll be negative 5 over 100. All right, so that's going to be what I put in the bottom of this fraction. So it'll be 1 over g prime of 7 is negative 5 over 100. Oh, I should simplify that. That's negative 1 over 20. Let me put that in instead of negative 5 over 100. And then if I do keep, change, flip, I'm going to do 1 times negative 20, which is just going to be negative 20. So negative 20 would be the slope of the tangent line of the inverse function at 1/2. So when I look at this function, it's actually the limit definition of a derivative, kind of a variation on that. And this question is one that you could possibly see on the AP test. So I'm trying to incorporate these AP questions more like in the actual lessons versus just doing them in the homework with you. So when I see the limit as h approaches 0 of arc sine of a plus h minus arc sine of a all over h equals 2, which of the following could be the value of a? So let's talk about what this really means. So the normal limit definition of a derivative for this particular function would be the limit as h approaches 0 of arc sine of x plus h minus arc sine of x all over h. But if you look, x has been replaced with this a value, and they're saying it's equal to 2. So essentially what they're saying is, what value could you put into the derivative of arc sine to make it equal to 2? So we do have to find the derivative of the inverse sine function first. So that's going to be what I focus on first. I'm going to be focused on finding the derivative of arc sine of just x. And then I'm going to figure out what value could I plug into that derivative once I get it, so that the final value of it is just going to be 2. So let's go ahead and find the derivative of this one. You have a formula for it. So it's going to be 1 over the square root of 1 minus x squared. Now, I want this to equal 2. So I'm going to have to do some work here to solve this equation, essentially. So I'm going to go ahead first, and I'm going to multiply like both sides by the denominator. So that would actually make it 1 equal to 2 times the square root of 1 minus x squared. Then I'm going to divide by 2 on both sides. So I'm going to have 1/2 is equal to the square root of 1 minus x squared. Then I'm going to square both sides, which would get rid of that square root. So I would have 1/4 is equal to 1 minus x squared. And I'm going to subtract 1 from 1/4, which would give me negative 3/4 is equal to negative x squared, which means 3/4 would be equal to x squared, which would mean that x would equal the square root of 3 over the square root of 4, which would just be the square root of 3 over 2. So that would be this value right here. So that would be an a value that you could evaluate the limit as. I mean, not the limit. You could evaluate the derivative at to give you a value of 2. All right, now this next question, if it'll switch, yep. This next question takes a lot of thinking, okay? And a lot of brain and thinking about all of these things and kind of putting everything together. So it says, let f and g be inverse functions that are differentiable for all x. If f of 3 equals negative 2 and g prime of negative 2 equals 4, which of the following statements must be false? So let's think about this. So it already told us that the derivative of g prime of negative 2 equals negative 4. All right, so if I'm trying to make any kind of conclusions about this middle one, because I can actually do something with the middle one because I know something about the function at f of 3. If I'm trying to find the derivative of f of x, it is the inverse of g of x. So it would be 1 over g prime of f of x, right? That's the formula there. If I evaluate that at 3, so if I was trying to find f prime of 3, it would be 1 over g prime of f of 3. And we know that f of 3 is negative 2. So it'd be 1 over g prime of negative 2. And g prime of negative 2 is 4. So it'd be 1 over negative 4. So we do know that that one 100% must be true because they're inverses of each other. Now, we don't know anything about 5 or anything about 0. But if if these functions are differentiable for all x, so they're going to be differentiable everywhere, both the function and its inverse. Okay, so the function and its inverse are going to be differentiable everywhere. Then, if both of the functions are differentiable anywhere, then neither of the functions can ever have a derivative that is equal to 0. Okay, and the reason that can never happen is because the derivative of an inverse function is the reciprocal, and that would put 0 on the bottom. So for example, if there is a place where f prime of x is equal to 0, so if there is a place where the derivative of f is equal to 0, then that means there would have to be a place where the derivative of the inverse is equal to 1 over 0. And that can't happen, okay, if it's differentiable everywhere. So that means that if the derivative is negative, it must stay negative. It must never turn positive, because if it turns positive, it has to cross 0. So if these functions are differentiable everywhere, both the function and its inverse, the sign of the derivative can never change if it's going to be differentiable everywhere. So that means that f prime can never be positive. So this one right here must be false. Okay? This one's definitely true. Okay? We know this one's true. This one could be true. But the only one that must be false is going to be 1, because technically, if both of the functions are differentiable everywhere, then the sign of one of them has to always be the same. So f can never turn positive, because if it turns positive, then that means it's going to be 0 somewhere. Okay? And then g prime is also negative, so both of them have to always be negative. This one's negative 4. That means these two are also negative. That means all of these functions have to always be decreasing functions. They can never turn positive, because then the derivative would turn positive. It would cross 0 somewhere in between, and that means the derivative of the inverse somewhere would not exist. All right, so which statements must be false? The only one that must be false is 1 only. Okay, that's the only one that must be false. 3 could be false. We don't know. 2 is definitely true, so it's not false. So 1 only is the only one that must be false. All right, so that's the end of lesson 3B.